Hey, morning everyone. So before I joined MRC Human Nutrition Research, I actually worked with Rebecca and Graziella at the MRC Unit for Lifelong Health and Ageing, and that's how I became involved with them and involved with Closer. So I've got a talk that's about 30 minutes. I may try and do it a bit quicker, but feel free to stick your hand up and ask questions at any point so it becomes a bit more interactive. So if I'm not speaking clearly or you don't understand anything, just stick your hand up. Okay. So this is taken from the Closer website and really explains what Closer is all about. And essentially, from my perspective, it's about capitalising on the huge investment made in the UK on a series of longitudinal studies. And to use data from different studies, variables need to be as comparable as possible. And a large part of Closer is this process of making variables comparable. And we call this harmonisation. Well, that's how I would define harmonisation. So with Rebecca, I worked on work package 1, which focuses on the harmonisation of biomedical measures. So it's this top one here. So my talk is really about the harmonisation of two simple measures, height and weight. So you may think, straightforward, height and weight, how difficult can it be? We'll find out that it isn't as straightforward as you might think. And I used the resulting data to investigate secular trends in obesity development, so secular trends in BMI age-related trajectories. The work was recently published in PLOS Medicine, so I'm advertising this here if you want to read the full paper. And I hope the paper and this presentation are a nice example of harmonisation of biomedical measures and cross-cohort analyses of longitudinal data. So I was trying to design a slide to show you why we're interested in cross-cohort analyses of longitudinal data, and I'm emphasising longitudinal data here. So we've got this here with age on the X and obesity on the Y. And we know from cross-sectional surveys that the prevalence of obesity at 4 to 5 years of age is about 10%. Okay, and I've got that arrow here because we know that over time this prevalence has increased. Okay, so if we looked in the 1980s, it was a lot lower than that. Okay, we also know at 10 to 11 years of age, the prevalence was about 20%, and that has increased over time. And in adulthood, the prevalence is about 25%. And that also has increased over time. Now, there's some evidence that the obesity epidemic in childhood is plateauing, but I'm ignoring that for now. These are the sort of current prevalence estimates in the UK as of 2012. So this tells us about the current obesity epidemic, the problem, what it is. But it doesn't mean that the prevalence of obesity or the risk of one person developing obesity develops like this over their life course. Okay? That's because there's between survey differences in the experience of the participants across their lives. And all of these between participant differences can be proxied by birth year. So we would expect that the adults here who had 25% risk today, okay, didn't experience the obesity epidemic until they were older. So they probably had much lower prevalence than 10, 20% when they were children. Similarly, the children here today experience the obesity epidemic very early in their lives, and as they move forward without effective intervention or prevention, they're probably going to have much greater risk than 25% when they're adults in the future. Okay, does that make sense? Okay. So my point really is that cross-sectional surveys only tell us so much. If we want to understand how obesity develops across someone's lives, we need longitudinal data. Okay. And if you want to understand how that longitudinal process has changed over time, we need longitudinal data on multiple cohorts who have been born at different time points. Okay. So I've got a slide sort of to emphasize this. So if what I said wasn't clear, hopefully this will clear things up. So it shows longitudinal data from two nationally representative UK birth cohort studies. One cohort born in 1946 and one born in 1958. Okay, so we can see that during childhood BMI as a, I don't want to say an indicator of adiposity, but that's what a lot of people use it for. Okay, but BMI increases rapidly during childhood. It's very similar for the two cohorts. Okay, but it's only when you reach into adulthood that the two trajectories diverge from each other, such that the more recently born cohort have greater BMI and thus higher risk for obesity. Now, this study and other similar studies in different countries have only looked at mean BMI. Okay, but we know from cross-sectional surveys that the obesity epidemic hasn't been because of a shift in mean BMI. It's been because of skewing of the distribution. So it's the upper end of the BMI distribution that's been driving the obesity epidemic. And it also, so these are just two of the studies in the UK. It doesn't include data from the more recent studies. Okay. And the rest of our knowledge on the obesity epidemic and secular trends in obesity trajectories is from studies where they've treated the longitudinal data as cross-sectional. They're not representative of the UK, or they only span a small part of the life course. So this figure shows data from the West of Scotland study. They had data spanning 15 to 80 years of age, and they had three cohorts, one born in 1930, one 1950, and one 1970. So first question, why are these data limited for investigating secular trends in obesity development from that figure? Yes. Oh God. Sorry to pick on it.
No,
Yeah.
it's fine. I mean, they're limited because they only overlap just kind of where the two lines.
Exactly. Yeah.
Overlap.
Exactly. So it's really that you can investigate secular trends here where there's overlap, but there's not so much you can do where there's no data for two cohorts. Okay, that clear? So ideally you'd have more of an overlap. Okay, so if you had data across the entire age range for all three cohorts, that would be ideal. Okay. So understanding sort of why we want to use cross-cohort comparison of longitudinal data and sort of the gaps in the literature, okay, the aims of our study are to investigate shifts over time in the distribution of BMI across age. So not just the mean, but the entire distribution, and shifts over time in the development of overweight or obesity across age. To do this, we use data from 5 studies. So you can see them here, the 1946 cohort, the 1958, the 1970, and the 2001 are nationally representative. Now there's a big gap between 1970 and 2001 when no new study was initiated. So we've used data from the 1991 ALSPAC study to fill in that gap. So I thought I'd jump straight in and show you the data. This is after a lot of work to get to this stage. There's 273,000 BMI observations on 56,000 white singleton participants in studies spanning births between 1946 to 2001 and ages from 0 to 64 years. So you can see there's a huge amount of data there. You can see some interesting results just from looking at this in the fact that sort of the prevalence here, the BMI sort of appears to be skewed over time at the top end. So if you look at the difference between the 1946 here and the 2001. But it makes you question, well, how can we use these? How can we analyze these data? Which was the next challenge. So I'm kind of wanted to show you the data, but I'm going to jump back a bit. Having seen the data, I'm going to throw it out there, it may be too early. What do you think the targets were for harmonisation? So put differently, why would BMI in one study or at one age be different to BMI in another study or at another age? Not because of something like, oh, there's a difference between sexes or there's a difference between ethnicities, but why would there be differences due to, say, something like measurement protocol or any guesses?
I don't know, availability of processed foods?
Yeah, so that's sort of something that we'd consider as an adjustment. So it's driving why there may be differences within the data, but in terms of the data collection itself, that wouldn't influence it. So I'm thinking of things. Exactly, yeah. Okay, so exactly. So the main one that we thought of was because of data may be measured or self-reported. Okay, so we know from previous publications that people who are overweight or obese tend to under-report weight, and that may introduce systematic biases in the data. So that's one, and that's probably what we thought was the major one. The second one is that there may be measurement protocol differences. Okay, so including if you're taking the weight of a newborn baby and they're naked or in clothes, that can influence the result. Okay, so if one study does one thing and one study does something else, that's going to introduce bias that we need to think about when we're harmonizing. And the final one is more nuanced, and in reality probably may not have a big impact on the data, but the precision of the instrument has been argued to be important as well. So the precision of the instrument is whether it was the data were collected to the nearest millimetre or centimetre or inch. And of course this will depend on whether the data were collected in imperial or metric.
Why should that matter? Because that would just change the measurement count.
Exactly. But if you've got something that's recorded to the to the nearest 1 millimetre or the nearest inch, which way you round those is going to introduce sort of systematic differences between the studies. Does that make sense? So there's this, without going into too much detail, there's this big bugbear of my old PhD supervisors that we shouldn't measure things to the nearest, it should be to the last completed unit. Okay. So yeah, these are the targets, and these are what we thought were the biggest targets for harmonization. And there's ways that we can rather than sort of applying arbitrary correction factors to the data, there's ways we can account for these differences within our analytical model. And at the end, I'm going to explain how we can do that very quickly. But in terms of what we did to produce a data set that would be usable for everybody, or anyone who wanted to go ahead and use these data, we applied sort of a soft touch, because the degree of harmonization may depend on what the researcher wants to do with the data and whether they want to incorporate some of the previous factors into their analytical model. So we did a lot of work just in extracting data, getting it into a usable format. We did things like, converting everything so it's on the same scale, kilograms and meters. We filled in missing data with self-reported data. So where there was measured data and self-reported data, if the measured data were missing, we filled it in with the self-reported data. We created exact age of assessment variables. We did other procedures like removing weights taken while a woman was pregnant, because that will influence differences between the studies. And finally, we ran a standardized data cleaning procedure. So each of the studies will have their own data cleaning, but we developed one ourselves. So we were applying the same to each of the studies, so the same limits. So in terms of the analyses, we used, don't worry if you don't understand these methods, they'll be self-explanatory when we come on to the results. But we used sex and study stratified analyses. So everything was done for each study separately and each sex separately. We used this procedure called LMS to describe BMI for age references. And essentially this process produces a growth reference chart like this one up here for each study and each sex. And then we modeled obesity or overweight trajectories using multi-level modeling. Okay. I think that's all I need to explain, except that, okay, so when we do the analyses separately for each study, we then produce figures that incorporated the results for all of the studies and all of the cohorts. And by looking across the different cohorts at the figures, we can get at secular trends in the obesity and the shifts in the BMI. So this is a table showing sort of the descriptive results. I'm going to skip it because it doesn't really tell you much, and there's a lot of information there. Yeah. Okay, so this is for our first objective, and this is just for children. Okay, so we've got males on the left here, females on the right there. Okay, we've got 3 different centiles that we've got for each study. So this is the 50th centile, the 91st, and the 98th centile. Okay, and we've superimposed the centiles on top of the IOTF cutoffs for overweight, obesity, and thinness, which you can see it all the way over there on your right. So the main results for this are that the 50th centiles are all in the middle of the normal weight range, which is indicative of good health. The centiles are all similar. Now there's a small shift here, okay, small upward shift, but you can see that it's very different to what the other studies have reported that looked at just mean BMI. And really what's driving the obesity or the increase in obesity over time is shifts at the upper end of the distribution. Okay, so here we can see that, you know, it's much higher up here for the 2001 MCS than for the 1946 NSHD. And this slide just shows that if we look at the lower centile, so this is the 2nd and the 9th, there's almost no differences. Okay, and these are the similar plots for adults. So of course in adults there's only 3 cohorts that have data at those ages. Those born in 1946, 1958 and 1970. And again we can see that although there's some shift in the 50th centile, most of the shift is occurring much higher up in the distribution. It's interesting to note that all of the cohorts at the 50th centile, so the median person, is developing overweight or obesity and shifting from this green band into the yellow band. Okay, so ideally all of these lines would run up horizontally in the green line, in the green band. Okay, but that age, the age at which someone enters the green band, enters the yellow band, has decreased over time, which suggests that there's the younger cohort, the more recently born cohorts are accumulating more exposure to overweight across their lives because they're entering into yellow earlier. Again, this just shows that at the lower centiles there's no real difference or very small differences. So these are the results for the second aim, that would investigate secular trends in obesity or overweight trajectories. These are the results for males. They're fairly self-explanatory. It shows that the probability of overweight, sorry, I'll just quickly explain. So this is probability of overweight or obesity, but that can also be interpreted as prevalence. So 0.2 could be 20% prevalence. Okay. So we can see that probability of overweight or obesity relevant to normal weight increased drastically across the life course, from as low as 0.1 at 10 years of age up to 0.7 at 64 years of age. And for the older 3 cohorts, there's this sort of stepwise decrease in time when the trajectories started to diverge upwards from each other. So from here to here, which again is indicative of this greater lifetime exposure to obesity risk. Now, if we look at the younger cohorts, these 2 here, even by sort of 10, 11 years of age, they have a much higher risk of overweight or obesity. This was estimated as an increase from 7.1% for these cohorts up to 25.8% for the highest one here. And then for the females, we see, you know, a very similar picture. So in terms of conclusions for the actual paper, our conclusions were that shifts in BMI have occurred at the upper end of the distribution, and in childhood this has contributed to a 3-fold increase in prevalence. But on top of that sort of shift, there's these age-related increases in adulthood that have led to the median UK adult currently being overweight. And essentially it means that more recently born cohorts are developing overweight or obesity earlier in their lives, and because they're developing it earlier in their lives, they're accumulating more exposure across their lives, And that accumulation of exposure is going to influence risk for things like diabetes and cardiovascular disease. So the strengths of what we've done are really the data. There's a huge amount of extensive serial data across a wide range of ages and birth years. And we've used what I think is a fairly robust analysis, not just focusing on mean BMI. There's some limitations, obviously. Main one is, well, one of the, I think is the main ones, is that there's the normal limitations of BMI. In that secular trend, we're assuming the secular trends have occurred due to an increase in adiposity, not fat-free mass, but we can't be sure with BMI. And of course, the measurement protocols, as we know from one of my first slides, weren't consistent across the studies. So some data was self-reported and some were measured. So there's two strands of sort of future research now that the data's there that we can start to think about. One is investigating the determinants and consequences of the secular trends. So one, what's driving this increase? Is it because there's been a change in diet or people are more sedentary? And two, what's the consequences? So does that increase in BMI result in higher rates of cardiovascular disease? And then the second one is more on the analysis. There's a possibility to use multi-level models that parameterize the measurement protocol differences. Okay, so rather than applying correction factors, because the data are measured or self-report, we can include that in our model, which I think is a much stronger technique. Okay. So this is an example. I've tried to make it as straightforward as possible. So imagine one person whose weight's been assessed across their life, 20, 27, 30, and so on. Okay, and then what we're doing is essentially just fitting a trajectory. Okay, but imagine that some of the data were measured and some of the data was self-reported. Okay, now this person has a high BMI, sorry, a high weight. Okay, and they'd underreported their weight at the ages when they were self-reported. So the red arrows represent where the data were measured, and the purple ones are where the data was self-reported. Okay. Now, in most models, you have one error term. Okay. But in the multi-level models, what we can do is we can have an error term if the data were measured and an error term if the data was self-reported. So we can include these differences within our analytical model. And I think moving forward, that's an area that is worth thinking about and researching more. So my overall conclusions, I guess, are straightforward. If we want to see how something changes over age, we need longitudinal data. Okay, that's one. And modelling those data to produce trajectories is a powerful approach to understand how something changes over age. Okay. Now, we can do that in multiple cohorts to see how a longitudinal process or the trajectories have changed over time. Now, the cohorts don't necessarily have to be born at different points in time. They could represent different geographical contexts or locations. And in that scenario, cross-cohort comparison tells us how the trajectories differ between different settings, perhaps because of different confounding, where there's different confounding structures. My final isn't meant to be negative, but it's just emphasizing that this process of harmonization and analyzing longitudinal data is complex, and it takes a lot of time and investment to be able to do it. But I'll finish by saying that it's worth it because it tells you a lot more than you'll get from cross-sectional surveys. And I'll finish there. Oh, no, wait, one more. This isn't a great slide. It's just to say that we've gone through the process. The data's all there now. It's been harmonized. We've got data sets where there's the variables that can be used for other analyses, and it's my hope that the data will be used more. And acknowledge the funders, and there's some links to the individual studies if you want to follow them up. Thank you.